Romilda Diaz Toledo Filho is a full professor of materials and structures at the Federal University of Rio de Janeiro, Brazil. He is member of the Brazilian Academy of Sciences. Researcher 1A agreed to the Brazilian National Council for Scientific and Technological Development and Senior Scientist of Rio de Janeiro. He is director of COPI UFRJ, head of the Sustainability Center for the Research and Education on Environmental Friendly Materials and Technologies of the Federal University of Rio de Janeiro. He is president of the Brazilian Society for Non-Conventional Materials and INBAR Task Force expert member, Bamboo Construction. He has conducted extensive research on vegetable fiber reinforced cement composites, bamboo bioconcrete, and rice husk ash and sugarcane biogas as mineral additives for concrete, nanomaterials and cement-based systems, fiber and textile reinforced concrete, and carbon sequestration and reuse of waste materials in building materials. Professor Toledo Filho is the author of over 250 peer-reviewed journal papers and over 390 technical articles published in conference proceedings. He has co-edited 5 book proceedings and published over 20 book chapters. He has coordinated over 75 R&D and I projects funded by governmental agencies and different industrial sectors. Please welcome Professor Romilda Toledo Filho.
Thank you very much for the kind introduction. It's a great pleasure to be here with good friends to talk about the use of concrete in different parts of the world. Thank you, and also to Nemi for the kind invitation. I would like to talk a little bit today about the use of bio-based materials. So I believe that there is a need for us to think about new solutions to reduce the carbon intensity all around the world. If you think here, if you look at this map, the global map, we see that only very small areas are in green, and this represents around or less than 50 tons of CO2 per terajoule, and we need to be below or around 20 tons of CO2 per terajoule to achieve, to be below the 2 degrees to reduce the world temperature, so that we can keep our climate objectives. And if we see here why this happened, is because our buildings are not very efficient. If we look all around the world, of course, developed regions, industrialized. If we see here North America, part of Europe, so we need heat in some of this country. We need cooling in some other areas. The buildings are not designed properly to work without energy. So there is a huge need to change the idea of designing. And if we think that in the coming years until 2050, we still need lots of materials to accommodate the migration of populations to the cities, and we expect that we have nearly 3 times more people living in cities in the coming years. I think we should think about natural materials as alternatives for construction. So I would like to show you this afternoon why these materials are not only good materials, but also they have conditions to reduce the intensity of CO2 and also to be more thermally efficient. So I would like to say that nowadays we need to think about designing thinking about circular economy. We also need to think about design for disassembling. We need to use building information modeling together with life cycle assessment in order we can achieve these goals. it's very challenging what we need to do for new infrastructure, but also to retrofit the existing one in order we can achieve our objectives. So I would like to show you here, I made a division based on the volume of natural vegetable fiber that we put in the composites. I could classify in 4 levels. So when we use the fibers as normal reinforcement or textile, we normally have less than 10% in volume as in the composition of the materials. But we can go to nearly 95% when we have bamboo pulp or bamboo industrialized as the main constituent. Then in this case, we can have up to 95% of biomass. And this is very important because the biogenic carbon can play a big role, and we can be even negative in emission if we use this material. In between, we have systems where we can have between 25 and 70% of biomass replacing a natural aggregate by vegetable aggregates and produce thermally efficient materials. Let me show you, I will show some of these applications and some of these developments that we are running here in Brazil. So let me start with natural fiber. I selected here 3 types. Curaua fibers, Amazonic fiber, the Curaua and jute, but also sisal fiber that is quite common in the northeast of Brazil, but also in Africa, in many other parts of the world. These are very high performance fibers. They can resist up to 500 MPa. They have elastic modulus that can range between 20 and 40. This is somehow in the same range of many synthetic fibers or even higher. So the jute fiber, for example, can have the elastic modulus that is similar to PVA fibers, and the other natural fibers have higher properties than polypropylene, nylon, and other synthetic fibers. These fibers, of course, needs to be designed properly. We need to think about durability. And one big issue is the use of CH-free matrices. So the matrix must be free of calcium hydroxide. To do that, we normally use pozzolanic materials. So pozzolanic materials like metakaolin or husk ash, silica fume. In the design, the important thing is that the CH-free matrix do not have calcium hydroxide in the composition, as it can mineralize the fibers. Just to show you the potential of these materials, I'm presenting here long aligned fibers, so it's built in layers. And when we test them in bending, we can see here a bendable concrete made with long aligned fibers. In this case, we have here 6 layers. We can achieve 25 MPa of bending strength, equivalent bending strength. But when we have short fibers, we can also have nice behavior, not as at this level of deflection, but we can have 10, 15 millimeters deflection with 7, 8 MPa or even 10 MPa under bending with short fibers as well. A big concern about the durability of these materials. We did some cycles of wetting and drying. This is a very to see how this material behave under changing the humidity and temperature. And we see here the necessity to use CH-free matrices. You see here in the left in this picture, if we do not replace cement by pozzolanic material to consume completely calcium hydroxide, after few cycles, even after 10 cycles, we can already see the decrease in the post-cracking behavior. And in the other hand, when we do use the CH-free matrix, we keep very much the same performance over the time. So you see here what happens in the Portland cement matrix with vegetable fibers. calcium hydroxide migrates to the microstructure of these fibers that are porous, and we have mineralization. So that's why we need to use metakaolin in order we can keep the fibers and the integrity of the fiber, like we can see in this microstructure here in this picture. Other important question is related with the temperature stability. Normally, people ask about how many degrees these natural materials can support. And we see here that up to 200 C, 250, up to this point, we do not lose much the mass of the material. So it's quite stable up to this temperature. And then we have a strong decrease in mass because we start the degradation of the chemical components of the natural fibers. And we see here when we test composites submitted to temperature up to 250 C, we see here that up to 200, we keep very much this beautiful post-cracking behavior under bending. So I would like to say that without no doubt, up to 150 C, we keep basically the same properties as the room temperature, and even up to 200, we still keep 75 to 80% of the properties of the normal material. One important thing is to see in tropical countries how the natural weather can, by thermal hydro cycles, affect the behavior of the material. When we have these tropical areas where we have a very, very quick cycles of wetting and drying, because we have rain and immediately after a few minutes, we have the sun coming out again. And then we have several microcycles that it's short term. Even in one day, we can have many of these cycles. And this can create can degrade the composite, because even the fiber do not mineralize. This is not the problem, but we can have a kind of fibrillation, fiber defibrillation, and we can lose the fiber capacity. But even so, if we see the post-cracking behavior, it's quite maintained. Of course, to improve this performance, to keep the original behavior, we need to use some sealant as well. So like materials like sealant or superficial coating, in order we can guarantee a longer term. This material, the structural cellulose structure of these fibers also can help healing of microcrack in concrete, and this was done using ultra high performance fiber reinforced concrete. We induced a thin crack under controlled crack under tension, and later we investigated the phenomenon of healing products growing in this crack. We see here that we could completely heal the crack due to the formation of cash and also other CSH products, and also calcite. So if we promote this porosity, inner porosity that the fibers can bring, it works, transporting water from one side to the other of the crack, and then deposition of materials, unreacted materials can happen. This is quite the case of ultra high performance materials where we have a large amount of cement, unhydrated cement, so we can close cracks. And we did some tests here just to see the interface of these steel fibers with these fibers. So where we have thin cracks, micro cracks, and you see here that the densification of the interfacial zone by these products completely healed the interface. And we did pull-out test after healing, and we see here this response. In some case, this is the non-cracked, the reference one. We can have in some case response that can go above this behavior, or very much keep the same force for pull-out. and after doing tests in healed and unhealed and uncracked materials, we also can see here that we have nearly the same response. This this red material here is a composite that healed. On the other hand, the other material in black here is a material that wasn't cracked. It was only kept under normal cure. The other system that is very interesting now, we are studying quite a bit, is the use of wood shavings materials, rust husk, and bamboo particles to be used as bioaggregate. One concern that we need to take care here is about the extractive that we need to remove. This extractive because it can affect hydration. And we can recover these extractives, for example, using reverse osmosis or in order we can keep the material. Then we can add value to this. The chemical industry can add value to this lignin. And if we don't do that, we have a quite retardation, as we can see in these calorimetric results here. If this is the just Portland cement, when we put the biomass without treatment, we retard it. But if we do osmosis treatment very much, even in some cases, we come back to the same heat of release and in the same rate as well. So these materials has nice workability. It can have compressive strength in the range of 15 MPa and very low density. These are materials that can have between 700, 800 kilogram per cubic meter with low thermal conductivity. So they can be used to improve the thermal efficiency of buildings. If we need even lighter material, we can also add, we can aerate this bioconcrete, making it even lighter, and then we can reduce even more the thermal conductivity. We tested, of course, these materials, they are sensitive to heat flux. We did some calorimeter tests to see the biomass, the number of seconds the biomass ignites. But when we use up to 75% of this biomass in the cement matrix, the cement protects the material and no ignition was observed. Other important aspect is about the biological durability of this material, because normally they have fungi, and we need to prevent fungal growth in the medium. So we identified for each biomass the kind of fungal that can be present in the biomass. And later we did the inoculation of the bioconcrete with these materials. We put this in a climatic chamber to simulate microclimate, and then to see if fungi could grow in the surface of these materials. But as you see here, even up to 90 days, no signs of fungi was observed in mixture that had 70% of biomass in the composition. Sandwich systems is already being tested using aligned fibers in the extremity composite. In the core, we are using lightweight bio-based concrete. And this material behaves very well. This is a work that I supervised together with Professor Joaquim Barros in a European project. And you see here very beautiful post-cracking behavior using this sandwich panel that now we are starting to plan to develop structural systems. So in terms of bamboo is a functional material. It has higher volume fraction close to the surface. So we need, if we wanna use this material as reinforcement, we should extract it, the strip close to the surface, because here you see here, the volume fraction can be 55%. If you come to the inner part, it's only around 30-35%. And this brings, so you need to obtain the strips taken from the part, and you see here that the elastic modulus and tensile strength of the strip when you take it from the outer part, can be much higher and much stiffer. The presence of nodes reduce the tensile strength, but of course it doesn't change much the elastic modes of the material. So we have to design taking this in account.
All right. Thank you, Professor. I just, in the interest of time, if you can get to your finish so we can stay on time, that'd be great.
So I use 1 minute to show you how these materials can work together with bioconcrete. We see here these materials, it has 20 giga and the bioconcrete too, so we can have very much the same system as steel and normal concrete. So these materials can have a nice tension stiffening behavior. So let me skip here some of these presentations about pole bamboo. Let me just come to the final 2 slides. You see here that the intensity of biomass is very important in order to reduce carbon emission, increase thermal efficiency, and of course, we need now to guarantee durability to these systems. So to conclude this presentation, I would like to say that the bio-based materials that are available all around the world can be a nice material as they are local and renewable. They can absorb and store CO2. They have capacity to reduce thermal conductivity, so they can be used to mitigate and also to adaptate climate change. Of course, it's needed to standardization and industrialization of these materials may be barrier that need to be focused. So it's very important to discuss this here at ACI, because we are already discussing this at Rylane as well at this moment. We need to design standard and design thinking about durability. Of course, to assess the emission potential of these materials is very important in order we can guarantee that this material can reduce emissions and be efficient in terms of energy. Thank you very much. This is my team that is working in some of these projects, and thank you very much for your patience.